So hey everyone, in this video we are going to learn the quick sort algorithm. Okay, so this is an algorithm which is similar to the merge sort, but it is much more efficient than merge sort. Okay, so this also gets solved by the time complexity of O of n log n, and when it comes to space complexity, this algorithm performs better than the merge sort. I'll tell you how is that. So by definition, quick sort is again a divide and conquer algorithm, just as the merge sort, and that works on selecting a pivot element. Okay, so I'll tell you what is a pivot element and partitioning the array into two subarrays. Okay, so whichever the elements that are less than the pivot element go to the left side, so the left subarray, and elements that are greater than the pivot go to the right subarray. Okay, so this actually happens recursively, and it is applied to both the subarrays, so the left and the right. And finally, as we keep doing that, unless we have just one element within each subarray, so we finally find that all the elements which we have are currently sorted. Okay, and then we just need to merge them into one single array. So let us see practically how can we implement the quick sort using this numbers. Okay, so I have considered this to be our example, and this is not my phone number, by the way. So just a bunch of random numbers which we have to sort using the quick sort. Okay, and the first step which I told you is that consider a pivot element. Okay, so usually pivot elements are considered from the start or the end of the array, or even you can consider any element if you want. So I'm just going to consider 4 as our pivot element. According to the definition, we have two subarrays. So like this, two subarrays, or all the elements that are less than 4 come under the left side, and greater than or equal to 4 come on the right side. So you see that 7 is greater than 4, we put 7 over here, and then 2 is less than 4, we put 2 here, and again 1 and 8 here, 6 as well, 3 comes here, 5 comes here, and then 9 and 4 itself. Okay, so if it is greater than or equal to the pivot element, so it also includes the pivot element. Let me just split this up. So I have just split these numbers. So now we have two subarrays, one is the left and one is the right, and again from these subarrays we need to again consider a pivot element. Okay, so let us always consider the last element to be the pivot, and of course you can just select anything if you want. So let us consider 3 as our pivot, and what are the elements that are lesser than 3 that should come to the left? So that is 1 and 2, and then 3 is the only left that is should come on the right. Sorry, 2 should come here first, since that's the first element. 2, 1 on the left side and 3 on the right side. So let's do the same for these numbers as well. So previously we had considered 4 as our pivot element, so this time let's consider 7. So 7 goes on the right along with 8. So 6, 5, 9 and 4. So 6 and 5 comes to the left like so, and right is on 9 is on the right, and then 4 on the left. Okay, so now let's again further split them into two subarrays. So here we can choose 2 as the pivot index. Okay, so where we can set 2 to the right and 1 to the left, and 3, you see that it doesn't have any it cannot be split into subarrays, right? So we just have 3 over here. So this is like our base case when we apply recursion. So if it has elements less than 1 or equal, then we just return that element itself. So over here let's now consider 6 to be our pivot, and since 4 was already considered, so we select 6 over here, and 5 and 4 come to the left like this, and over here let's consider 9 this time. So 9 comes to the right, and then 8 should come to the left and along with 7. So 7, 8. So you see that it's still we need to keep on doing unless we have one single element. So here we have two elements, here we have two elements, and again we further need to split them out. So here we can consider 5 to be our pivot index. So 5 comes to the right and 4 comes to the left. Then we have 6 here, and then 7 and 8. Okay, so here we can consider 7 and then 8, and then finally 9. So here we see that finally when all the elements are split, where we just have one element within the subarray, so we finally see that our numbers are sorted. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so I hope you understood. So let me just recap. First we consider the pivot element, and then create subarrays left and the right. based on if it is less than or greater than the pivot element. Okay, so again we keep performing the same operation by selecting a pivot element and then splitting the array into lesser than or greater than, even for the subarrays, until we find just one element within each subarray, and that's when we get all the elements that are sorted over here. Okay, so and of course we can just select any pivot element we want. Usually it is preferred to select from either start or end of the subarray. Okay, so the time complexity of this sorting algorithm is O of n log n, just as the merge sort, so O of n log n, and this has slightly better space complexity when compared to merge sort, because we don't have to create all those subarrays when creating that recursive function. So basically it creates an array, right? Because once we split them, again we need to merge them into one single array. Okay, so again that also takes another space complexity by joining all those arrays, and then we delete that array. So that's why that is slightly inefficient in terms of space complexity, but here it is better. Okay, so the best case is O of n log n, so the worst case could be O of n square. Okay, so basically when we choose a wrong pivot, so when we choose a wrong pivot, we will keep doing this again and again, so we'll be having a long tree like structure. Okay, so that's when we find that the worst case is O of n square. So this is the best or the average, and this is the worst. Okay, let us now practically code this inside JavaScript. Alright, so I've just created a function called quicksort, and by passing in these numbers just as we saw in the example. So let us start by creating the base case for our recursive function for the quicksort. So let's put in array dot length. If that is less than or equal to 1, then we just want to return the array itself. Okay, so now let's go ahead and calculate the pivot element. So by default, let's say it is at the last index, so basically the last element. So let's put it in a constant called pivot and set that to array at the last element. So array dot length -1, and then let's initialize the two empty arrays for the subarrays, basically the left subarray and the right subarray left, and set that to an empty array, and let's do the same for the right as well. Alright, so now we just want to check. So based on the pivot element, we split the array into left and the right subarrays. So for that, let's iterate through the numbers that we have. So let's say for let I equals 0, and then I is less than array dot length, and here we can just -1 because we do not want to count for the pivot element, because we will be combining everything into one single array. Okay, because it could be possible that we are considering the same pivot element again and again, right? So that's why we don't include that over here. You can just exclude that by -1 and then increment I. Now we can just put a check if the element, if that is lesser than the pivot element, then we just want to push that to the left side. So left dot push the array at I, and else we want to push it on the right. Alright, so once that's done, we can now combine the left side and then the right side and call the recursive function quicksort, because we want to calculate the pivot index and again split them into left and the right subarrays. Okay, so let's return directly. So let's first of all spread across whatever we are returning from the quicksort, because this, otherwise if we do not use a spread operator, it would become an array of arrays, which we do not want. So let's set quicksort and then pass in the left, and here we need to include our pivot index. Okay, because we excluded them here, and then let's spread across the quicksort whatever is returned from the right subarray. So right, sorry, this is a function, right? I need to use common brackets, and here as well. Okay, so now let's run this file. This function is returning me all the numbers in a sorted order. Okay, as you see over here, so we are passing in these numbers which are unsorted and we are getting it in the sorted form. So this is all about the quicksort algorithm. So I hope you understood. It's fairly easy to implement when compared to the merge sort, to be honest, because we just have fewer lines of code, because in merge sort we had to create another recursive function which is to merge the sorted arrays. So here we do not do all of that jazz. So this is fairly simple, and of course it performs better than merge sort when it comes to space complexity. So this is all about the quicksort, and this is mostly the last algorithm which we are going to discuss. There are many other algorithms and they are not as popular as these 5 that I showed you. Okay, so I'm not going to cover them all. Alright, so I guess that's it for this sorting algorithms series. So thank you so much for watching. If you like the series or if you like the video, please give it a like and subscribe for more videos just like these, and I will see you guys in the next video.